Distributed Systems from Scratch. This is episode 10, Fault Tolerance. This episode is different from the ones before it. We're not learning a new algorithm or a new theoretical framework. We're learning a mindset, how to build systems that expect to break and handle it gracefully. By the end, you'll have the 6 patterns every senior engineer reaches for when production catches fire, including the one Netflix uses to break its own systems on purpose. Werner Vogels, the CTO of Amazon, has a famous line: everything fails, all the time. That's not pessimism, that's engineering reality. At scale, failure is not an exception, it's the steady state. Something is always broken somewhere. A disk is failing, a network link is flapping, a process is stuck, a deploy went wrong. The question isn't, will something break? It's, what breaks next and how does the system cope? Let me show you why failure is inevitable at scale. A single server with 99.9% uptime, 3 nines, is down for about 8.7 hours per year. Sounds manageable. But if you have 1,000 servers, each at 99.9%, on average, one server fails every 9 hours. You wake up, a server has failed. You go to lunch, another one fails. Before dinner, another. At 10,000 servers, you're dealing with multiple failures per hour, every day. Google has estimated that about 2% of hard drives fail per year. At their scale, that's thousands of drives failing every single week. Failure at scale isn't a bug, it's arithmetic. Before we can handle failures, we need to classify them. What kind of failure are we dealing with? The answer determines which techniques apply. There are 4 failure models from weakest to strongest. Crash stop. The node stops and never comes back. It's dead forever. This is the simplest model to reason about, like unplugging a server from the wall. Crash recovery. The node crashes but eventually restarts. It might recover some state from durable storage, a write ahead log, for example. This is the most common model in practice. Raft and Paxos both assume crash recovery. Omission. The node is alive but drops some messages. Maybe a network buffer overflows and packets are lost, or a congested switch drops frames. The node looks partially alive. It responds to some messages but not others. Byzantine. The node can behave arbitrarily. It can send wrong data, lie about its state, or actively try to sabotage the system. This is the hardest model. Blockchain consensus, aviation systems, and space systems are designed for Byzantine faults. Most distributed systems assume crash recovery. Byzantine fault tolerance is expensive and only used when the threat model demands it. Here's the fundamental problem of failure detection, and it's the same problem we introduced in episode 1. You cannot tell a slow node from a dead node. You send a message, no reply comes. Is the node dead? Is it overloaded? Is the network congested? Did your message arrive and get processed, but the reply was lost? All failure detection in distributed systems is ultimately based on timeouts. And timeouts are just guesses. Set them too short, and you'll declare alive nodes as dead. Set them too long, and you'll waste time waiting for truly dead nodes. The most common failure detection mechanism is heartbeats. A monitor sends periodic pings to each node. The node responds with a pong. If a node misses enough pongs in a row, the monitor suspects it has failed. But look at the diagram. The third ping gets no response. Is the node dead? Maybe. Or maybe the network is slow right now. Or maybe the node is in a garbage collection pause and will respond in a moment. The monitor can't be sure. All it can do is start a timeout and see if a response eventually arrives. A smarter approach is the Phi accrual failure detector, introduced by Hayashibara and colleagues in 2004 and used by Cassandra and Aka. Instead of a binary alive or dead verdict, it outputs a suspicion level, phi. It tracks the history of heartbeat intervals and builds a statistical model of what's normal for this node. If the current interval is slightly longer than usual, phi is low, probably just variance. If the interval is wildly outside the normal range, phi is high, likely dead. A phi of 1 means there's about a 10% chance this is a false alarm. Phi of 3 is a 0.1% chance. Phi of 8 is virtually certain. The application chooses the threshold that matches its tolerance for false positives. Aggressive detection, low threshold, means faster failover but more false alarms. Conservative, high threshold, means slower detection but fewer false positives. Pattern 1, timeouts and exponential backoff. We introduced this in episode 2. Now let's go deeper. When a request fails, you retry. But how long do you wait between retries? Fixed interval, say retry every 200 milliseconds, is dangerous. If the server is overloaded, hammering it every 200 milliseconds makes things worse. Exponential backoff increases the wait time with each retry. First attempt, wait 200 milliseconds. Second, 400. Third, 800. Fourth, 1600. Fifth, 3200. After 5 attempts, about 6.2 seconds of waiting in total, give up. The service is probably truly down. The formula is simple. Delay equals the base times 2 to the power of the attempt number plus some random jitter capped at a maximum delay. This gives the failing service breathing room to recover. Jitter is critical and often overlooked. Without jitter, imagine 1,000 clients all failing at the same time. Maybe the server just restarted. They all wait exactly 200 milliseconds and retry simultaneously. Then all wait 400 milliseconds and retry simultaneously again. This is the thundering herd problem. Synchronized retries create periodic traffic spikes that can recrash the server. With jitter, each client adds a random offset to its delay. The retries spread out over time. The server sees a gradual trickle instead of a wall of requests. AWS's architecture blog recommends full jitter. Instead of adding a small random amount, pick a random delay between 0 and the calculated backoff time. This maximizes the spread. Always add jitter. Always. Pattern 2, idempotency. We first saw this in episode 2. Now let me show you the full engineering pattern. Here's the complete flow. A client sends a payment request with an idempotency key, a unique identifier like a UUID. The server receives the request, checks its idempotency store. Have I seen key ABC-123 before? No, this is a new request. Process it, charge the card, and store the key along with the result. Now the response is lost in transit. The client times out and retraces with the exact same request and the same idempotency key. The server receives the retry, checks the store. Have I seen ABC-123 before? Yes. Return the cached result. Charged $50 without processing again. No double charge. The key is stored durably. Even if the server restarts, it remembers which keys it has seen. Stripe, PayPal, AWS, Google Cloud. They all implement this pattern. Every mutating API that can be retried should be idempotent. Pattern 3, the circuit breaker. This one is about protecting yourself from someone else's failure. A circuit breaker has three states, like an electrical circuit. Closed. The normal state. Requests flow through to the downstream service. The circuit breaker counts failures. Everything is fine. If failures reach a threshold, say 5 failures in 10 seconds, the circuit opens. Now all requests are immediately rejected without even trying to reach the downstream service. Fail fast. This protects your system from wasting resources on a service that's clearly down. After a timeout period, say 30 seconds, the circuit moves to half open. It allows one test request through. If that request succeeds, the service is recovered, close the circuit, resume normal traffic. If it fails, the circuit opens again. Why does this matter? Look at the top half of the diagram. The world without a breaker. Service B is slow. Service A keeps calling B and every call just hangs. Look at A's thread pool. completely blocked 100%. Now A can't serve its own clients. The timeout spread upstream. One slow service and the whole call chain is dying. Now the bottom half. Same slow service B, but A has a circuit breaker and the circuit is open. A fails B request instantly. No waiting, no blocked threads. Its pool stays healthy and it keeps serving everything that doesn't need B. The failure is contained. That's the entire point of the pattern in one picture. Pattern 4, bulkheads. Another isolation pattern, but at a different level. Without bulkheads, all your outgoing calls share a single thread pool. If one dependency, say the recommendation service, becomes slow and consumes all threads, every other dependency is blocked too. Login, search, checkout, all dead because recommendations is slow. With bulkheads, each dependency gets its own thread pool. Recommendations pool fills up, only recommendations are degraded. Login and checkout use their own pools and remain completely unaffected. The name comes from ship design. Ships have sealed bulkhead compartments. If one compartment is breached and floods, the bulkheads contain the water and prevent the entire ship from sinking. Same principle. Contain the failure. Don't let one dependency sink the whole system. Pattern 5, graceful degradation. When something fails, do less, don't do nothing. This is a design philosophy. When a component fails, the system should still provide value, just reduce its value. Recommendation service down, show popular items instead. Not as personalized, but the page still loads and the user can still shop. Search index lagging, serve slightly stale results, better than refusing to search at all. Payment service overloaded, queue the charge and confirm asynchronously. Don't lose the order. Image service down, show placeholder thumbnails. The content is still readable. The key insight, most features have a degraded mode that's much better than no mode at all. Design those degraded modes in advance. Don't discover them during an outage. Pattern 6, chaos engineering. Don't wait for failures to find you. Go find them first. Netflix pioneered this approach with Chaos Monkey, a tool that randomly kills production instances during business hours. If your system can't survive one dead instance, you find out on a Tuesday afternoon with engineers watching, not at 3 a.m. on Black Friday. Netflix expanded this into the Simian army. Chaos Gorilla kills an entire availability zone. Chaos Kong kills an entire AWS region. Latency Monkey injects a network delays. Each tool tests a different failure mode. On the database side, Kyle Kingsbury's Jepsen framework tests distributed databases under network partitions and node failures. It has found consistency bugs in nearly every major distributed database: Cassandra, MongoDB, CockroachDB, Redis, Elasticsearch. If your distributed database hasn't been Jepsen tested, you should be nervous about what it might do under partition. The principle behind chaos engineering: the best time to discover a failure mode is when you're ready for it, in controlled conditions, with engineers actively watching. Let me put the full toolkit together. 6 patterns. Timeouts with exponential backoff. Don't wait forever. Idempotency. Retry safely. Circuit breakers fail fast when a dependency is down. Bulkheads isolate failure domains. Graceful degradation. Do less, not nothing. Chaos engineering, break things before they break you. The unifying design philosophy from the SRE mindset. Assume everything will fail. Make failure boring. A failure should trigger automated responses, not panic. It should be an expected event with a known playbook, not a surprise. Let's recap. 1. At scale, failure is the steady state. Design for it proactively, don't just handle it reactively. 2. Exponential backoff with jitter prevents thundering hertz. The jitter is essential, always add it. 3. Idempotency keys make retrieves safe. Store the key, check it before processing. This is the standard pattern for every mutating API. 4. Circuit breakers contain cascading failures. Bulkheads isolate failure domains so one slow dependency doesn't take down everything. 5. Chaos engineering finds failure modes before your users do. Test in production, under controlled conditions, with engineers watching. Next episode, distributed transactions. How do you ensure atomicity when a single transaction spans multiple nodes? Two-phase commit was the original answer, but it has serious problems. The saga pattern is the modern alternative. We'll explore both, plus serializable snapshot isolation. That's episode 10, Fault Tolerance. 6 patterns for building systems that embrace failure instead of fearing it. We've now completed the halfway point of the series. The foundation is solid. Everything from here builds on what we've covered. Next time, distributed transactions. Thanks for watching.